Hello and welcome to the Daily Space for today, October 17th, 2018. I am your host, Dr. Pamela Gay, and I am here to put science in your brains. So we have a whole variety of stories to go through and also a few announcements. We're getting ready for some big changes here around our CosmoQuest stream, and we're going to have to take next week off on hiatus in order to prepare everything that is coming. So, you'll have me today, tomorrow, Friday, then we're going to take off until November 1st, and we're coming back November 1st with a lot of awesome things that we think all of you will appreciate. So, with that announcement set aside, let me go ahead and get started with today's news. So in my first story for today, I have a story of giant acrylic tanks. There are some stories that you read and you're like, this doesn't look that interesting. And then you keep going and you realize it's kind of cool. So it turns out these acrylic tanks that kind of look like giant fish tanks are indeed strong enough to contain all the liquid you might want to put into them, because they're going to get filled with linear alkabenzene. This is a chemical that is used to detect weird particles, neutrinos, and if the scientists have it right, even dark matter. A former gold mine in Lead, South Dakota. That's right, a gold mine in a city named Lead. A former gold mine in the city of Lead, South Dakota, is getting used as a construction site for the new Lux Zeppelin experiment, or LZ experiment. That is two different acronyms that are being combined into a new third acronym. The LZ experiment is designed to search for one of the prime candidates for dark matter particles. We know, at least we think we know, that dark matter is made up of particles by looking at how massive galaxy clusters interact. When we look at these systems, we see that the stars, the gas, the dust all end up physically interacting with one another as these systems slam into each other. Now, while there is essentially collisions, ram pressure stripping, a variety of different physical effects that come from the collision of these systems, what we don't see is the dark matter interacting. In fact, the dark matter of systems appears to pass through one another without any interactions at all. So, in looking for dark matter candidates, what we're looking for is an essentially more or less collisionless particle. And one of the prime candidates is a weakly interacting massive particle that should occasionally interact with the linear alkabenzene in just the right way to emit a bit of light. Now, these acrylic tanks that are going to be built and delivered to the former gold mine in Lead, South Dakota, these tanks will be surrounded by detectors capable of catching that rare slight flickering that may occur with such an interaction. With each of these tanks, the acrylic also acts to help protect the alkabenzene from having other kinds of particles of the more regular kind getting in and triggering light through interactions. in this way, by burying things underground, we're able to shield the detectors from one whole suite of particles that might otherwise create noise in our attempts to detect dark matter. And the use of this extraordinarily thick acrylic is going to work to, well, help us block out a whole variety of other possible sources of noise. So sometimes you need a giant acrylic tank put in the bottom of a gold mine in Lead, South Dakota, in order to detect dark matter. Now, moving on to a more planetary kind of story, this is a theoretical image of what a migrating massive planet might look like in terms of how it interacts with the surrounding particles in a protoplanetary disk. Astronomers now have the capacity to get amazingly high-resolution images of disk systems in the process of forming planets around young stars. This is getting done on a regular basis with the Atacama Large Millimeter Array down in Chile. What we don't always know is how to interpret the nuances that we see in these results. And what we hadn't previously known is how to look at these images and figure out if we can detect planets in the process of migrating. Well, new research is helping us understand exactly what to look for. This is research that is coming out of Warwick University, and what they're looking at is how different sized particles will interact with a migrating planet in different ways. What is found is massive particles are able to move quickly, migrate with a planet, whereas smaller particles will tend to get caught up and end up on the interior of the planet's motion. This means that when we look at systems and we see a pair of rings indicative of different sized particles, we can assume that there's some sort of planetary motion taking place. The interior smaller particles and the exterior larger particles should indicate motion. To quote from the press release on this discovery, it says, research models show that the exterior dust ring will contain more large dust particles because they move at a higher velocity and are fast enough to keep up with the planet as it orbits inwards. The inner ring consists of small particles because they move inwards more slowly than the planet. Consequently, they are unable to get out of the way of the inwardly migrating planet. Now we know what to look for, and here's to hoping that ALMA allows us to understand just how frequently planets migrate through their systems. This will help us further constrain our planetary system formation models. We know that our models don't do the best right now. As I talked about yesterday, we're constantly finding new systems that current models don't anticipate, such as the 4 massive hot Jupiters that were discovered and discussed in yesterday's episode. Now, this gives us one more thing to look for and one more constraint that we will hopefully be able to use in the near future. Now, in the next story I have, we're looking at an amazing comparison image. Researchers are working to use the moon to block out different parts of the radio sky to allow them to take very detailed images and correct those images for foreground objects and sources of noise. Now, what is happening is researchers are, in this image, taking a whole series of images of the moon and measuring how bright the moon appears in radio light. What we're seeing is the radio emission from our Milky Way galaxy getting reflected off the moon. Now, the reason that how the moon reflects radio light is getting observed is astronomers want to use the moon as a comparison source to tell them just how dark is the sky. This is one of those things in astronomy that's remarkably hard to explain. We do a lot of really complex comparisons, and sometimes what you want to do is look at a source, measure the source, look at the sky, measure the sky, subtract the sky from the source, and that gives you the true brightness of an object. Now, where you get into trouble is when what you're actually trying to observe is the brightness of the sky in general, because if you're trying to measure the brightness of the sky in general, or in this case, the radio brightness of the early universe all across the sky, you don't have a comparison source to go to. So since you don't always have that ability to go on the object, on the sky, what astronomers are looking to do instead is go on the object, on the moon, and use the moon as that comparison thing to say, this is what the noise looks like. Now, since the moon does reflect radio signals from the Earth, it reflects radio signals from the galaxy as shown here, they had to carefully observe the moon and figure out how to subtract off all of that reflected radio noise to get an understanding of what is just the darkness that they can use to correct. Now, using these observations, this isn't the science I'm showing you. This is the comparison data I'm showing you. What they're hoping to do, and the paper that was published is strictly a proof of concept. This is research that's coming out of the Astra 3D project and was just published in monthly notices of the Royal Astronomical Society. What they're looking to do is measure the sky in radio using an interferometer that allows them to combine the light from a whole variety of different radio disks to get an extremely sensitive, high-resolution image. They're going to make these observations when the moon is not in front of the part of the sky they're looking at. They're then going to make the exact same observations, same basic sidereal time, same basic local time in terms of how high things are up in the sky. When they do this with the moon in the way, it tells them, okay, so here is our background noise. That's what we see on the moon. Let's subtract that off of the observations we made of the sky. And this should let us see the background distant initial radio emission of the universe. Now, this is super complex and super amazing comparison images, and this is where we start to see just how creative we have to be sometimes to do science. These astronomers realized there was no good comparison data, and so they're like, okay, we have a moon, and the moon gets in the way periodically. Let's just use that in the way moon to get our comparison data. Now, so far, all they've done is a proof of concept. They've published their proof of concept. Things look good so far, and I really look forward to seeing what happens as their research proceeds and they begin to measure more and more of the earliest radio emissions from the first days of our universe. Now, continuing on through our observations, I now have a story of, magnetic fields. This is research coming out of USRA that utilizes data from the Sophia Airborne Observatory. Sophia is uniquely capable of examining the sky in infrared radiation with high-resolution detectors capable of doing things like measuring the polarization of light. This is how light gets aligned as it scatters off different kinds of objects. Now, the cool thing about polarized light is if you have a magnetic field aligning particles, aligning dust in a given region, that aligned dust will end up producing aligned light if you look in polarized, look at it through polarization filters. With the Surveyor Airborne Observatory, astronomers looked at one of the nearest active galactic nuclei, Cygnus A. This is a system where the black hole in the center is actively feeding on material. And as it feeds, some of the material in the accretion disk is so hot that it is, as it orbits round and round the black hole, it's charged particles. These charged particles are then in turn generating strong magnetic fields. These strong magnetic fields are in turn generating jets. And it's the jets that appear in the image in the upper left-hand corner here, where we see these amazing radio lobes that are interacting with the surrounding material in the universe. Now, down in the center, where we can't generally zoom in, what I'm showing you is an artist's rendition of what the accretion disk, a torus of material around that supermassive black hole, might look like. Now, exactly how this torus gets shaped, exactly how all of the material gets confined into this innermost region of the active galactic nuclei, this has been something that theorists have worked to explain using magnetic fields, but up until now, we haven't had observational confirmation. Using new data from SOFIA, looking at polarized light, astronomers were able to see the distinct signal that indicates the dust in this disk is shaped by magnetic fields. This brings us one step closer to confirming that our theoretical understanding of how Seyfert Type 1 and Seyfert Type 2 galaxies, how active galactic nuclei, how quasars, all are one unified kind of object that are simply seen from different angles and with different black hole feeding rates. This observation brings us one step closer to observationally confirming the entirety of this model and saying, yes, we do understand how the inner workings of these very amazing systems are actually working. So this is a day where we're going to see lots of partnering between the theorists and the observationalists working together to prove and eliminate our theories and help us know, yes, we do understand our universe. Now, in a purely observational story, we have new results coming out of the Cosmos project. Some of you may remember a number of years ago when scientists were able to come out with their first ever observational understanding of the three-dimensional structure of dark matter. In this amazing observational program, a myriad of different telescopes on the Earth in space, working across a variety of wavelengths, very carefully mapped out the slight mutation that appears in the shape of galaxies when their light gets bent by intervening dark matter. And by looking at these distortions in the shapes of galaxies, astronomers were able to map out these distortions must be triggered by this intermediate dark matter. If I look further away, I'm going to see a different set of distortions, and those are created by a new set of intervening dark matter. Well, all of these deep observations could also be used to look at amazingly faint, distant objects. And using this data and new data that has been taken since then, astronomers were able, using the Very Large Telescope, to zoom in on the oldest supercluster of galaxies ever observed. This system looks like nothing that we see in the nearby universe. This galaxy cluster is lumpy and bumpy, and the structures aren't tightly formed. Scientists believe that this is because we're seeing it as it's still coming together, whereas when we look at the Virgo supercluster and other superclusters in our nearby universe, we're looking at systems that have had the fullness of time to gravitationally pull themselves together and have the structures become much more finely shaped. Here, we're looking at it just as things are coming together. And we're seeing basically a baby picture of what our Virgo cluster might have looked like early on in the universe. This system has been named Hyperion, and it's just kind of amazing to realize this is the kind of science that is going to be, if it ever launches, done on a regular basis and much faster by the James Webb Space Telescope. We can do the science today. It just takes more observing time to do it with the Very Large Telescope here on Earth. And we can't go into all the colors of the infrared that we'd wish to go into using ground-based telescopes because the atmosphere just gets in the way. But this is a start of letting us see what kind of science is to come when and if JWST ever gets launched. Okay, so moving on, we have one final story for today, and this is a look ahead. This Friday, if everything goes well, at 10:45 p.m. Eastern, we are going to have a launch of a new set of spacecraft on their way to Mercury. This is the Bepi-Colombo mission, and it consists of two different spacecraft that are going to be tied together for their journey to Mercury. One of these is a JAXA craft. The other one is built by the European Space Agency. Both spacecraft are going to launch together, if everything goes well, on an Ariane 5 rocket and fly away to eventually help us understand in higher resolution than ever before the surface of Mercury. They are also going to work to map out the magnetic fields in this area so close to the sun. We're all looking forward to the science that will hopefully come from this mission. As always, don't count your missions before they return data, but everything right now looks wonderful. And here's to hoping that we have an amazing rocket launch from French New Guinea this coming weekend. So that's all I've got for today, and I will now take all your questions. Please go ahead and at me in the chat. I already see that we have a question from Hanny Zvorverp. They're asking, and thank you, Fenmil, for the subscription. And I heard other cheerful noises earlier on. Can we light up the chat for Fenmil and Scott Bragdon for their subscription renewals and for all the other wonderful things that have been happening during this episode? So Hanny is asking, is there a wide range of frequencies in the infrared? Are there distinct scientific things that can be done in each wavelength? This is a question I could spend 45 minutes answering all by itself. So the truth is, infrared radiation refers to an entire range of frequencies. Thank you, Keeper Maps, for the bits. Let's get some more rockets in the chat. So across this entire range of colors, we can see various emission and absorption lines that come from a variety of atoms and molecules. This is made more complex by the fact that the exact color that atoms and molecules emit and absorb light, that's fixed for where they are. But if those atoms and molecules are moving relative to us, the color these transitions take at will appear to shift. If something's moving away from us, it will all shift into the red. Thank you for the bits, K-More. Also, Trekker Kev, let's get more rockets in the chat. So with the shifting of light, the earliest things to happen in our universe, because our universe is expanding, they've gotten shifted into the red. So things that happened at high energy wavelengths, in the ultraviolet even, they're going to get shifted all the way into the infrared when we try and observe them from here on Earth. So when we look at the earliest days of our universe, even the hot stuff that's happening ends up in the red parts of the spectrum. Thank you, Bad Panda, for the subscription, and thank you, Scott, for the bits. Let's just keep lighting up the chat. Thank you so much. So I see another question coming in from Space TV Net. In some publications, such as New Scientist, they report that virtual black holes have been created using sound instead of light, and they use them to study Hawking radiation. I haven't read those articles. My gut reaction is that's crazy talk. Now, my gut reaction isn't necessarily accurate. It is my gut's reaction without doing math or looking at the science or considering what they're saying. Now, all that said, acoustic waves have been used to create extraordinarily condensed packets of atoms and molecules. This is generally done in order to see if people can create room temperature fusion. This is the kind of stuff that you might have heard about in movies like The Saint. Now, currently it's fiction. We are able to highly condense particles using acoustic waves, but haven't so far been able to produce more energy than went into the system. So far, haven't necessarily been able to produce fusion. I haven't heard of this producing black holes. I don't read everything. I don't have a subscription to New Scientist. I probably should get one. So I haven't heard of this. I need to read the article. I don't have a subscription, so I can't. My gut says no. My gut could be lying. Sorry for the overly honest answer. So someone whose name is hard to read on my screen. Let me see if I can. Herleu, thank you, Herleu, for your question. Says, how do we use the moon data in the future as a base metric for object luminosity? So, the way this works is we measure how bright the moon is. We wait for the moon to be in front of the object, and that's when we make those observations of the moon. When the moon is not in front of the object, we measure how bright the object is, and then we subtract what was measured with the moon from what was measured without the moon, and we use that to tell us how bright above background an object is. Now, brightness and luminosity aren't the same thing. Brightness is how many photons we're receiving from an object, and luminosity is how many photons that object is giving off. Now, a 100-watt light bulb is giving off the same number of photons, presumably, if they're all built the same, no matter where I put it. But I'm going to perceive that 100-watt light bulb as brighter if it's right next to my eyeball and fainter if it's further away. So if we want to get to luminosity, we need some way to figure out how far away an object is. And the moon doesn't help us get to that piece of data. So in this case, what the moon allows us to do is measure brightness above background, where we use the moon to get at how bright is the background, so we can subtract off that background. Luminosity, that's a much more complicated calculation to do. It's okay, Paranor. Times are going to get screwed up sometimes. And yes, thank you, everyone, for everything, exactly what Guido said. Anytime, Herleu. So let's see, are there any other questions in the chat? I've got 2 minutes left before we hand this channel over to Dr. Matt Richardson, who's going to be coming to you with Astro 101. As a quick reminder, we are going to be on hiatus starting Sunday up until November 1st. When we come back on November 1st, we're going to have some amazing surprises, and we hope that we're going to have a much improved, experience for all of you out there in the audience. So stay tuned for those changes, and remember, we won't be here next week. We will be back the day after Halloween. So Beppu Colombo is being done as a collaboration between the European Space Agency and the Japanese JAXA Space Agency. Yeah. Anyways, as a parting reminder before I hand this over to Matt, this is a collaboration of the Astronomical Society of the Pacific, the Planetary Science Institute, and Youngstown State University. Give us a follow, they're free, and find out when we're going to go live with new content. We are sustained through your subscriptions, and every bit really matters. Now I'm going to take off, but following me will be Dr. Matt Richardson with Astro 101, so don't go anywhere. So wherever you are in the world, have a fabulous morning, evening, or afternoon. And remember, get outside and look up. Bye-bye.